Hello and welcome to this revision session on periodic motion for AQA A-Level Physics. So in this revision session we're going to review the concepts of periodic motion. So the following topics of circular motion, simple harmonic motion, simple harmonic systems and force vibrations and resonance are on this particular revision session. So the first topic we're going to look at is circular motion. So the topic of periodic motion focuses around the physics of circular motion. So an example of this would be the moon Phobos orbiting Mars. Now you've got to be aware that angular motion is another name for circular motion. Now when you've got any object orbiting in a circular path, they have two velocities. You've got the angular velocity, which is the rate at which the object moves in a circle, but you've also got tangential velocity, the rate at which the object moves in a straight line. Now another name for tangential velocity will be linear velocity, which is the quantity which you called velocity previously. Now throughout its angular journey, an object's tangential velocity is always changing direction, as shown in the following images. Now this concept can lead to our understanding of forces in the application of circular motion, the mechanics of circular motion. So any object undergoing circular motion will experience a centripetal force. A centripetal force is a name given to the overall resultant force experienced by the object. Now we only consider the resultant effect of the centripetal force. So it's important to note that any object undergoing circular motion will always have a resultant force towards the center of the circle. So let's consider the motion of the Earth around the Sun. Now technically planets move in an ellipse around stars due to gravitational effects, but we'll consider that it's moving in a circular path. Now the planet will always have a direction of motion tangential to the star. So as it orbits, the Earth in this instance changes direction because it's moving in a circle. So this means that its tangential velocity is changing because its direction is changing. So therefore this tells us that the planet or the object is accelerating. Now if there is an acceleration, there must be a resultant force. This is from Newton's second law of motion, F equals ma. Now remember, acceleration and this force are directly proportional. Now the resultant force which causes circular motion is called a centripetal force. So the force always acts towards the center of the circle of rotation. So we can consider that the Earth is being constantly dragged towards the center of the Sun due to gravity, because the centripetal force is a center-secant force. But you will get a circular path and not being pulled towards the center due to another effect, because any object such as a planet will want to move in a straight line in the same direction unless a resultant force acts on it. This principle is called inertia. Now this concept was covered in the previous mechanics module. It's Newton's first law of motion. However, the centripetal force always acts towards the center of the orbit. So the centripetal force acts perpendicular to the path of the motion of the object. Now this is actually an important definition, because any force which acts perpendicular to the motion of the object it is acting upon becomes a centripetal force. Now we'll actually cover many different forces acting as a centripetal force in AQA Physics Paper 2, such as the magnetic force, the electrical force and the gravitational force. So as this force acts at right angles to the motion, it cannot affect the speed of the motion. So this is an important idea in physics. Centripetal forces cannot change the speed of an object because centripetal forces change the direction of the object. Centripetal forces cause acceleration by changing the path of the object, not the speed. So therefore we can say centripetal forces cause acceleration by deflection. So the combination of inertia and the centripetal force combine to form the path of circular motion. So the centripetal force provides an acceleration towards the center of the orbit, whilst inertia prevents the body from falling into the center. So therefore we can say the centripetal force and inertia combine to ensure the object follows a circular path. Now before this was known, physicists thought that a circular force must cause circular motion, much like how a linear force causes linear motion, which we call the centrifugal force. But now we know this does not exist. Centrifugal forces are fictitious forces, so it's incorrect physics. So the centrifugal force is actually the representation of the combination of inertia resisting the centripetal force. So this means that if the centripetal force was removed, so in this context the sun disappeared, the object that is in orbit would move in a straight line in the same direction. It would move off in a tangent. So it would revert back to the laws of linear mechanics as opposed to circular mechanics. So as we mentioned before, when we consider angular motion, we've got to consider two types of velocity. We've got the linear velocity and we've got the angular velocity. Now the linear velocity is the rate of displacement in a straight line, whilst the angular velocity is the rate of displacement in a circle. Now we can measure the rate of displacement in a straight line as a length, but we can measure the rate of displacement in a circle with an angle. So to calculate the angular velocity, we've got to consider angular displacement. So we can notice that when we are doing our work, we've got to have a change in angle. Now to do this, we actually work in radians. So the SI unit for measuring an angle is considered as in radians. Now a radian is the angle made by an arc equal to the radius of a circle. So the circumference of a circle is known to be 2 pi r, where r is equal to the radius. So this implies that 2 pi arcs with the length of the radius would fit in the circle. So this means we can deduce that there are 2 pi radians in a full circle. So it's important to know that in one complete rotation, that which is 360 degrees, it's also 2 pi radians. Half a rotation, which is 180 degrees, is pi radians. A quarter of a rotation, which is 90 degrees, is pi over 2 radians. So therefore 1 radian is equal to 360 over 2 pi, which is 57.3 degrees. Now in this course you've got to be able to convert from radians to degrees and vice versa in things such as angular motion, but in also phase differences of waves. So let's consider how you would convert from degrees to radians. So to convert 45 degrees into radians, you say radians is equal to degrees times by 2 pi over 360. So it'll be 45 times by 2 pi over 360, which is pi over 4. However, you can give answers in terms of pi when doing theoretical work. However, if you're doing practical work, you can't do this because this implies a zero level of uncertainty. So in experimental work, you'll have to place answers to the correct number of significant figures. Now let's look at how you would convert from radians to degrees. So to convert 2 pi over 7 radians into degrees, you would say degrees equals radians times by 360 over 2 pi. So it's 2 pi over 7 times by 360 over 2 pi, which works out to be 51.4 degrees. So as we talked about before, we've got our linear or tangential velocity, which is the velocity of the object moving in a straight line, whilst the angular velocity is the velocity of an object moving radially, how quickly it turns in a circle. So we can define the instantaneous linear velocity to be the velocity the object would have travelled in a straight line if the centripetal force was removed, which we give the symbol v and we measure in meters per second, whilst the angular velocity is the angle through which the radius of the circle turns in 1 second. We give it the symbol omega and it's measured in radians per second. Now we can therefore say that the angular velocity is the rate of change of angular displacement, or the angle covered every second, which is equal to theta radians over t seconds. So we can then measure this in radians per second. Now we can use the equation of angular velocity to derive an equation for the linear velocity. So when we work this all through, as you can see on the screen, we can see that the equation which links angular velocity and linear velocity together is linear velocity is equal to radius times by angular velocity. Now the theory of behind angular motion was first derived by Sir Isaac Newton when he imagined the idea of being able to place something in orbit of Earth, as this would lead to circular motion, which led to a very, very famous thought experiment and allowed us to understand orbital motion, which was called Newton's cannon. So if we consider the following: if we throw a ball out horizontally and it falls to the ground some distance away, gravitational attraction will pull it to the Earth. A rifle bullet fired faster but also horizontally reaches the ground after a kilometre or so, which tells that all objects are attracted to the centre of the Earth due to the gravitational attraction between the object and the Earth. So our object is acting like a projectile. There is only the force of gravity acting on it. Now let's consider firing a bullet so fast that it covers an appreciable part of the Earth's circumference before it reaches the ground. Now if you fire it fast enough and it gets faster and faster and faster, it falls over the edge of the Earth. So the Earth falls away from the bullet's original direction at exactly the same rate as the bullet falls. So gravitational attraction is still acting downwards, however the Earth is falling away from the bullet as it does this, which means the bullet never hits the ground. So this would occur due to the curvature of the Earth. Now this means that the bullet will keep falling over the edge and go around the Earth and keeping just above the ground until it arrives back at the starting point and hits us from behind. So therefore this is called the orbital speed. So this is the speed required to reach a stable orbit around a body, and this speed is a lot lower than the escape velocity. Now that's an important idea to consider. So you've got to remember that the orbital speed is the speed needed to maintain a stable orbit, and the escape velocity is the velocity needed to overcome a gravitational field. Now we say it's achieved in orbit because the bullet is in free fall, because the bullet is now falling but there's nothing there to catch it. It's fallen freely. So the bullet will experience a centripetal force towards the centre of the Earth because the combination of the centripetal force and inertia produces a circular motion. Now, this means the bullet will never hit the Earth and the bullet will never experience weight. Why is this? Well, the force of weight is acting on the bullet, but it doesn't experience it as it doesn't hit the surface to experience the reaction force, which is how we interpret weight as humans. So, Newton imagined that if he threw a stone fast enough, it would orbit the Earth because it was always falling towards the Earth at the same rate as the Earth falls away from it. The projectile becomes a satellite. So orbital motion is projectile motion under the condition of free fall. Orbits are produced by the body being orbited falling away from the orbital rate with the same rate as the acceleration as the centripetal acceleration. So this is an important idea. So the satellite accelerates towards the Earth, but the Earth moves away from the satellite, so the falling satellite never hits the Earth, so the satellite is therefore in orbit. Now all objects in orbit have a centripetal force of weight acting on them, but they don't experience this force due to the lack of contact with another surface. Now frequency is the number of complete revolutions that occur every second. Now for one complete revolution we know that the change in angle is 2 pi radians. So if we substitute this into the angular velocity equation, we get that omega is equal to 2 pi over t, where t in this case is the time period, the time taken for one complete rotation or revolution. Now we can also say from a previous concept in physics that frequency is equal to 1 over time period. So therefore we can link these two equations. So we can link the time value in the angular velocity equation and the frequency equation. Now the equation on the right is the equation for the frequency in all situations, as frequency is the number of events per second. So we can substitute the frequency equation to work out the link between angular frequency and angular velocity. So we can therefore say that omega is equal to 2 pi f, or f is equal to omega over 2 pi. Now you need to be able to convert between angular velocity and angular frequency. They're very closely linked. Now for any conversion to work, angular velocity has to be in radians per second, not degrees per second. Now this equation is given to you in your examination book, so you'll need to memorize the term of each thing in there in the equation and the units of each term. Now it's important that you learn these equations off by heart to help, and in addition you would need to know how and when to use each equation in different situations. So let's look at an example. A wheel is turning at a frequency of 20 revolutions per second. Calculate the period and angular velocity of its rotation. So the first step is to work out the time period. So t is equal to 1 over f, so t is equal to 1 over 20, which is 0.050 seconds. So therefore we can say that to work out the angular velocity, we say angular velocity equal to 2 pi f, or 2 pi over t. So therefore it's equal to 2 pi times by 20, or 2 pi over 0.050. Either way, your answers is going to be 130 radians per second. Now, the centripetal force must be a resultant force. We know this because the object is accelerating, so therefore there must be a resultant force on the object. We know this because the tangential direction of the object is constantly changing in the motion, so the velocity of the object is constantly changing. Now we know this because our tangential velocity, as noted in our diagram, is not always pointing in the same direction. Now, since F equals ma, the object must accelerate in the same direction as the resultant force, because circular motion is an application of Newton's laws, and Newton's laws still work in circular motion. So this tells us that the resultant force must be acting towards the center of the circle of rotation. So this is a result of Newton's second law of motion. The acceleration must be acting towards the center of the circle, as shown in these different images. So the acceleration provided by the centripetal force is called the centripetal acceleration. So the centripetal acceleration of an object always has a direction from the body to the center of the circle. So this means humans on the surface of the earth experience a centripetal acceleration towards the center of the earth, which is provided by the gravitational attraction between the human and the earth. So it tends to be 9.81 meters per second squared. Now there's actually a further centripetal acceleration produced by the spinning of the earth, which has a centripetal acceleration of 0.034 meters per second squared. So this is actually a very small effect compared to the actual centripetal acceleration produced by the gravitational attraction, so you would still be attracted to the center of the earth if the earth stops spinning. Now the centripetal acceleration can be derived if we look at a segment of the path taken by an object moving in a circle. So consider the change in velocity v when it's moving angle subtended from the center of the circle, given as delta theta. So we can therefore say that in times of t, the object changes velocity by delta v and changes angle by delta theta. So in a certain time, the linear and angular displacement will change. So therefore we can say that delta theta equals delta v over v. We'd use from the small angle approximation, so it only works for angles of 10 degrees or less. So you can work it all the way through by subbing in our equation from GCSE physics of acceleration equals to change in v over t. So you can work this through and we get an equation for centripetal acceleration of it equal to v times by omega. Now if we use v equals r omega, we can derive three different equations for acceleration. A is equal to v omega, or A equals r omega squared, or A equals v squared over r. Now you'll be given at least one form of the equation in your equation book. Now each equation can be used for any situation, but you've got to choose the one most suitable given in a puzzle. Now you must memorize the units of each quantity, and remember it always acts towards the center of the circle of rotation. Now what we can also do is we can work out an equation to work out the resultant force by saying F equals ma and work out A and sub it into that particular equation. Now we can use this process as circular motion is an application of Newton's laws of Newtonian mechanics. So we can say F is equal to mv omega, F equals m omega squared r, or F equals mv squared over r. Now again, you'll be given at least one form of the equation in your equation book, and each equation can be used in any situation. And remember, this is the equation to calculate the resultant force acting towards the center of the circle. So from looking at these centripetal force equations, you can see the factors affecting this resultant centripetal force are the mass of the object moving, the linear velocity at which the object moves, and the distance from the center of the circle. So when considering a situation, these are the only factors which affect the centripetal force. All other factors do not affect the centripetal force produced, because there's no other term in the equations. So what we can say is that this is the resultant force, which is for an object moving in a circular path and it acts towards the center of the circle. If the force is removed, the object would move off at a tangent with a linear velocity. So we can now actually calculate this value. Now what we can also say is we can equate it to other forces found in a situation, because the centripetal force is always defined as the resultant force towards the center of the circle. So in this instance we can say the resultant force towards the center of the circle is r minus t. So we can therefore say mv squared over r, or mr omega squared, or mv omega is equal to r minus t, which you can do in a variety of different situations. You can then allow terms to be cancelled through, and then you can work out values. So if you said that the centripetal force was equal to mg, we could say mv squared over r equals mg. We can then cancel values through and work out a value for g. Now what we can do is that this process works for all forces which act as centripetal forces. So for all situations you must determine the resultant force, equate it to the centripetal force equation, then rearrange it into the appropriate format. So what we can say is as follows. Okay, we can say that the resultant force, the centripetal force, acts at right angles to the direction of linear velocity. So the definition of centripetal forces is that it must act perpendicularly to linear motion of the object. So therefore the centripetal force cannot affect the linear velocity of the object. Now we can also prove this by considering the laws of energy conservation covered in mechanics. So we know that work done is equal to force times by displacement. However, because the centripetal force is perpendicular to linear motion, no work is done by the centripetal force on the object because there's no displacement in the direction of the force. So as no work is done, the kinetic energy store of the object remains constant and the orbital speed stays constant. So we say the orbital path is on a line of equipotential. It's the line where the energy store of the object does not change as it moves along the line. So if an object moves along a line of equipotential, no work can be done, which is why objects can achieve stable orbits in the universe. So for a fields aspect, we state the orbit, if something like the moon, is in a line of equipotential as no work is done when moving along its path. Now in the examples covered previously, we've only considered where one force is acting as the centripetal force, but in reality there are a number of forces that act as a centripetal force on an object. So you need to resolve the forces in different situations, then apply the equations of circular motion. So as we know that the centripetal force is a resultant force acting towards the center of the circle, and we can work it out with following equations. Now it's important to note that these equations are true for any situation. So what you can do is, like we said before, is use this principle to solve complex problems involving circular motion. So in this instance, a car doing a loop-to-loop has the reaction force acting upwards and the weight acting downwards. So the first step is to draw a diagram of the situation. Now don't forget that the centripetal force is the resultant force on the object. This means we need to consider what the overall force towards the center of the circle is, because the centripetal force is always the resultant force towards the center of the circle. So you find the direction of the centripetal force, you then resolve the forces on the object. If the force is in the same direction as the centripetal force, it's a positive. If the force is in the opposite direction as the centripetal force, it is a negative. So in this instance, we would say the centripetal force is equal to reaction minus weight. We equate the unresolved forces and the centripetal force. So we now say mv squared over r is equal to big R minus mg. And we substitute in values for each force and calculate the wanted value. So in this instance, if a car's at the top of the loop, we can say weight is acting towards the center and reactions acting towards the center, and centripetal force is acting towards the center. So therefore the centripetal force is equal to weight plus reaction. So mv squared over r is equal to mg plus r. So therefore a challenging physics question would sometimes require you to resolve forces into different components. But remember, it's the forces which only act perpendicular to motion which are considered in the centripetal force derivation. Now in most situations, the centripetal force acting horizontally, so you'd have to work out the horizontal component of each force. Now, so what do you do to solve complex situations with the centripetal force? Well, you would firstly draw a diagram of the situation, find the direction of the centripetal force, resolve the forces on the object, equate the resolved forces and centripetal forces, substitute in the equations for each force, and calculate the wanted values, ensuring you give your answer in standard SI units. Now, resolving centripetal forces allows you to consider the forces on objects moving on surfaces at an angle. Now the most common example of this are vehicles moving on a bank curve where the slope of the road helps you negotiate the curve. So what you would do is, in this situation, you would resolve the forces on the object. So you look at the situation and you say, in this instance, n sine theta, which is the horizontal component of n, as you can see from the diagram, is equal to the centripetal force, as the centripetal force is the resultant force acting towards the centre of the circle horizontally. Whilst in the vertical there is no centripetal force, as that's in the horizontal, but there is the vertical force of gravity. So you then say n cos theta, the vertical component of n according to this diagram, is equal to mg. We can then combine the two equations to eliminate n and get an expression for theta as desired. So you would say that, well, mg sine theta over cos theta equals mv squared over r. Now you can work that through, and therefore we can say mg tan theta is equal to mv squared over r, because sine theta over cos theta is therefore equal to tan. We can cancel through our values of m, so we get tan theta is equal to v squared over rg, so therefore theta is equal to inverse tan times by v squared over rg. Now again, this tells us that a large theta will be obtained for a large v and a small r, so roads must be steeply banked for high speeds and sharp curves. Now also friction helps, as it allows you to take a curve at greater and lower speed than if a curve is frictionless. But interestingly, the angle of banking does not depend on the mass of the vehicle. In the next part of the video, we're now going to look at simple harmonic motion. So if we place an object in simple harmonic motion by a displacement of x, there will be a force that brings the object back to the equilibrium point. Now we call this the restoring force, and it always acts in the opposite direction to displacement. The equilibrium point is where the object comes to rest in the simple pendulum at its lowest point. So we can represent this mathematically. So we can say that F is directly proportional to minus x, or A is directly proportional to minus x. So this tells us that the minus sign is that the acceleration is acting in the opposite direction to the displacement. So both of these tell us that the acceleration and the restoring force are directly proportional to the displacement equilibrium in the opposite direction, which is the same principle as shown previously, that the resultant force and the acceleration always act in the same direction. Now either equation, F is directly proportional to minus x or A is directly proportional to minus x, can be stated as the condition required for an oscillator to be acting as a simple harmonic oscillator. Now what we would say is, for an object to be moving with simple harmonic motion, its acceleration must satisfy two conditions. Condition 1, the acceleration is proportional to the displacement, but that's the second condition is that the acceleration is in the opposite direction to the displacement. The acceleration acts towards the equilibrium position. Now we can consider the acceleration in simple harmonic motion to be a restoring acceleration, as it always wishes to bring the object back to the equilibrium position. So these are the two conditions needed for simple harmonic motion to occur. So we're now going to consider the equations of simple harmonic motion by looking at the motion of a pendulum. So if a pendulum is carrying out simple harmonic motion, then it must have a restoring force directly proportional to the displacement from equilibrium in the opposite direction. So to fully analyse this motion, we're going to consider the cycle of one pendulum. Now in this example, we've defined left as negative displacement and right as positive displacement, but this is completely arbitrary. So one cycle of a simple harmonic oscillator is the equivalent to one cycle of a wave, or one rotation of circular motion. So this tells us that the phase difference of one cycle is equal to 2 pi radians, or 360 degrees. Now different oscillators can have different phase differences. Now oscillators therefore can have a phase difference, which is how much an oscillator lags behind another oscillator. So we define one cycle as the pendulum bob being displaced in the negative direction when at point 1, being released in swinging through point 2 at maximum speed, then it reaches point 3, comes to a complete stop, then swings in the negative direction to reach a maximum speed at point 4, then complete a full cycle when it stops at point 5. So what has happened? In point 1, there's a maximum displacement in the negative direction, then it's got a zero displacement from equilibrium at point 2, then it's got a maximum displacement in the positive direction at point 3, Then at point 4 we've got a zero displacement from equilibrium, before then getting to point 5 where there's a maximum displacement in the negative direction. So that's one complete cycle. Now the pendulum starts its motion at a maximum displacement A for amplitude. So what then happens is the displacement is 0 at equilibrium. Then at the maximum displacement there, it's got a maximum displacement in the opposite direction, so minus A. And at this point it's back to equilibrium, so the displacement is 0. Now it's important to note that the body has inertia, so it always keeps moving past equilibrium position even if it wants to be at equilibrium position. Then it returns back to its maximum possible displacement of A. So if we consider the displacement of a pendulum or any simple harmonic oscillator against time, we will get the following graph, which can be shown in this particular animation of a mass spring system. So this looks familiar to a type of mathematical graph. So an object carrying out simple harmonic motion plots out a cosine curve for a displacement time graph, indicating the cosine function must be present in the term to describe displacement. So the displacement of a bob x after time t is given by the equation x is equal to a cos 2 pi ft. Now remember that the maximum displacement possible by a pendulum is a. So this means that the object displaces more and more, and cosine 2 pi t over t becomes closer to 1, where t is the time into the cycle and big T is the time for one complete cycle. So it's an important idea, but we've got to use the small angle approximation for this equation. So therefore we use radians, and it can only be true when the angle of displacement is 10 degrees or less. Now again, this equation for displacement is given to you in your equation book. You don't need to memorize it, you just need to understand what it shows. Now if you consider the displacement of a simple harmonic system with circular motion, you can see that actually there are similarities between the two. Now we can calculate the phase difference between two oscillations in simple harmonic motion. The phase difference is the angular difference for the displacement between two successive oscillations. Now this will only work when the oscillators are coherent. They have the same frequency and wavelength and the same phase difference. Now again, the phase difference can be considered the difference in swing cycle between the two pendulums, which is shown in the following animation here. Now, if we consider a pendulum displaced by x, we know that we've got a velocity of 0 at the maximum displacement, because at this point, at this instance, the actual oscillator has stopped moving. Now, as the pendulum moves through the equilibrium position, the velocity is at its maximum. This is because there's no longer a restoring force on the object as it's at equilibrium. So this means due to F equals ma, there is no acceleration on the object. Now, the object continues to move through equilibrium as it has inertia at this point. Now objects carrying out simple harmonic motion still obey Newton's laws of motion. So at this point, when it gets to the maximum displacement A, this tells us the velocity is returned to 0. This is because at this instance it has stopped moving. Now it can't accelerate, then it gets back to the equilibrium, once again reaching maximum velocity because it can't accelerate it because there's no force on the object. Once again, the object moves through equilibrium as it has inertia at this point, and then it returns to 0 velocity at maximum displacement. So you can now consider when you've got maximum displacement, you've got minimum velocity, and when you've got minimum displacement, you have maximum velocity. So we can use this particular idea to work out the equation of the velocity of the bob at a displacement x. So v is equal to plus or minus 2 pi f or omega times by a squared minus x squared. Now the plus or minus sign represents the back and forth motion of the pendulum. Now maximum velocity occurs at the middle of the swing when the displacement is 0. So x is equal to 0. So this allows us to simplify the equation to say v is equal to plus or minus 2 pi f or omega times by a, which is the maximum possible velocity for the object. Now again, these equations are given to you in the equation book. You don't need to memorize them, you just need to be able to understand what they show and when to use them. Now let's consider acceleration. So at a maximum displacement of minus x, the acceleration is a maximum because the resultant force and acceleration are proportional to the displacement, but they act in opposite directions. So when you get to equilibrium position, because because the displacement is 0, the acceleration is 0, as the resultant force is 0. Then once again, when you get to maximum displacement, you will get the acceleration and force as a maximum, but in the opposite direction, back towards the equilibrium position. Once you get back to equilibrium position again, the displacement is 0, so therefore the acceleration and resultant force are 0. Back to our maximum displacement again, and the acceleration and resultant force will be acting back towards the center of the oscillation swing, the equilibrium position. Now remember, the displacement and acceleration are always proportional to each other, but in opposite directions. This is indicated as one term has a plus value and the other term has a minus value. So the velocity of the oscillator is always the opposite compared to the displacement and the acceleration of the oscillator. Now the acceleration of the bob at a displacement of x is given by the equation. A is equal to minus omega, or 2 pi f squared, times by x. Now this makes sense, as we originally said A is directly proportional to minus x. So this minus is important because the acceleration acts in the opposite direction to the displacement. So what we can now say is, if we want to work out the maximum acceleration produced by the object, we now know that x would equal A, so therefore the maximum acceleration is equal to minus 2 pi f squared, or minus omega squared, times by A. So it makes sense because we know that A is directly proportional to minus x, so A is equal to minus omega squared x. So the proportionality constant is going to be omega squared. Now again, these equations are given to you in your equation book. You do not need to memorize them, you only need to show what they are and when to use them. So we can summarize our simple harmonic equations as the following. So you've got your displacement, your velocity, and your restoring acceleration, both as a general equation and as its maximum value. Now these equations are given to you in your equation book. You don't need to memorize them, only to use them. Now you do not need to you just need to understand what they show and when to use them. So you've got your equation to work out the displacement from equilibrium at a particular time in the motion. You can work out the maximum possible displacement from equilibrium. You can work out the velocity at a particular time in the motion. You can work out the velocity at the equilibrium position in the motion, the maximum possible velocity. We can use the equation to work out the acceleration at any point in the motion, and finally use it to work out the acceleration and maximum possible displacement. Now in all simple harmonic systems, there is a conversion between the kinetic energy and the potential energy. Now all undamped oscillators are considered closed or isolated systems. So a closed system is a system where energy does not enter or leave, so therefore the total energy of the simple harmonic system remains constant. So we can say that the total energy of the system is equal to the kinetic energy store of the oscillator plus the potential energy store of the oscillator. So the total energy of a simple harmonic oscillator can also be referred to as the mechanical energy of the system. So let's consider a pendulum. So its potential energy store is due to this position in the gravitational field, and its kinetic energy store is due to the oscillator moving. So at this point, maximum displacement, the pendulum has highest point, so it's got maximum gravitational potential energy, whilst it's therefore got no motion, so it'll have zero kinetic energy. At this point, it's moving through its fastest, so at this point it's got a maximum kinetic energy store. The restoring force has done work on the object, allowing the energy to change store. Here at maximum displacement, the pendulum has highest point again, so it becomes a maximum gravitational potential energy store. Here it'll become its maximum kinetic energy store, and once again here its maximum gravitational potential energy store. So as you can see, as it's a closed system, the total energy of the system remains constant throughout the cycle. Now as we know, when you get a maximum gravitational potential energy, you'll get the minimum kinetic energy, and vice versa. Now remember, we can say that because it's a closed system, the total energy store of the oscillator remains constant throughout the cycle. In reality, this is an assumption because energy is lost to the internal energy of the surroundings. So we can see here how the energy stores of the oscillator changes as part of the cycle. Now the process which transfers energy from the mechanical system, the oscillating system, to the internal energy of the surroundings is called dampening. So what we can say is it's unlikely an oscillator will ever actually truly truly have zero kinetic energy or gravitational potential in a cycle. So what we can do is we can look at this concept with another simple harmonic oscillator, a mass on a spring. So with a mass on a spring, it follows the same laws of physics as the pendulum. Now there are two types of potential energy stored in a mass spring. You've got gravitational potential energy and you've got elastic potential energy, while you've still got the kinetic energy store of the particular mass spring system. So let's consider one cycle. So at this point at equilibrium, the object is not stretched, so it has elastic potential energy store at a minimum, but will still have a gravitational potential energy store, and because it's moving at its maximum speed, it will have its maximum possible kinetic energy. When you get to this point here, the spring has been fully extended or stretched, because it's a negative, because it's been completely compressed. So it's got a maximum elastic potential energy store, and its gravitational potential energy is as maximum as it's at its highest, but it's not moving at this point, so its kinetic energy stores at a minimum. Once again, at this point it's not stretched, so you can see that the elastic potential energy is a minimum, the gravitational potential energy is still present, and the kinetic energy stores now moving as its highest because it's moving at its fastest. At this point, the spring is completely stretched, so at this point its elastic potential energy is at its maximum, its gravitational potential energy is at its minimum because that's the lowest point, and its kinetic energy store is also at its minimum because it's stopped moving. So we can see our combinations of energies. Now this graph combines the elastic and gravitational potential into one potential energy store. So you can see what's happening in the top, in the middle, and then at its lowest point. So what we can see is it's very similar to the energy displacement of a simple pendulum, because when you've got maximum potential, you've got minimum kinetic. And again, this assumes no energy is being lost to the internal energy store of the surroundings. It assumes that there's no dampening forces acting on the oscillating system. We're now going to look at simple harmonic oscillating systems. So we're going to apply our understanding of simple harmonic motion to two different systems, both of which have simple harmonic oscillators. So we're going to consider the mass behind the mass spring system firstly, and then we're going to consider the simple pendulum. So what we can do is we can consider that the force placed on a spring is equal to k times by x, which was covered in GCSE physics and mechanics as Hooke's law. So we can then say T is equal to minus kx. So therefore we also know that A is equal to F over n from Newton's second law. So A is equal to minus kx over n. So it indicates to us that A is directly proportional to minus x, indicating that it follows simple harmonic motion. So if a mass on a spring undergoes oscillation with an acceleration given by A is equal to minus kx over m, and we also know that's carrying a simple harmonic motion, so that A is equal to minus omega squared x, we can equate the two and derive to make omega the subject. We also know that omega is equal to 2 pi f, so therefore we can rearrange it and make f the subject before we can say f is equal to 1 over t and rearrange it to get the following equation. T is equal to 2 pi times by the square root of m over k, which is the time period for one oscillation. So it's the time it takes for a mass spring to complete one whole cycle. So this equation is given to you in your equation book, but you've got to be able to understand what it shows. Now it also allows you to work out the spring constant of a spring, which is the second way of calculating this value from experimentation, with the first way being shown in the mechanics module. So this tells us there are no other factors that affect the time period of a mass spring system apart from the mass and the spring constant, and these are the only two factors, as they're the only two factors in the equation. No other factor is found in the equation, so therefore there is no other thing which affects the time period of the mass spring system. Now it's a very important idea, and you can also use this equation to derive the spring constant from experimental results. So we can use the mass spring system equation to work out the spring constant of the system. So to do this, you've got to change the mass placed upon the spring, then measure the time period of an oscillation of a spring. You can then plot the following results on the graph of t squared against mass, and we know that if t is equal to 2 pi times by square root m over k, t squared is equal to 4 pi squared over m times by m over k. So So as this is a straight line of best fit, we know y equals mx plus c, where y equals t squared, x equals m, so therefore the gradient m is equal to 4 pi squared over k. So we know, so therefore spring constant is equal to 4 pi squared over gradient. Now this also tells us that if we plotted t squared against the amplitude of oscillation, you would get a straight line like so, because the amplitude of oscillation does not affect the time period of the oscillation, as it's not found in the time period equation. So therefore we know that the time period for the mass spring system is equal to t is equal to 2 pi times by the square root of m over k. So therefore t is the time period for an oscillation of the mass spring system, m is the mass of the system in kilograms, k is the spring constant of the spring in newtons per meter, and then 2 pi is the constants. Now again, this equation is given to you in your examination book. Now the assumptions for the equation are that the spring is an elastic material and there is no dampener acting on the oscillator. Any factor not in this equation cannot affect the time period of the oscillation of the mass spring system. Now you can change the mass of the mass spring system, you can then measure the time period of one oscillation and use this to derive the spring constant of the spring. Now the next thing we're going to look at is a simple pendulum. So to understand the mathematics of the simple pendulum, we consider a pendulum bob of mass m on a light string of length L at an angle of theta to the vertical. Now what we can do is we can displace it and derive our forces with our resultant force Ft acting towards the equilibrium position. Now the only force acting in the horizontal is the horizontal component of the weight, which must be providing the resultant restoring force of our pendulum. So our restoring force is equal to the horizontal component of the weight, which is equal to mg sine theta. And once again, we know that A is equal to F over m, so therefore we can say A is equal to minus g times by sine theta, as we've popped it into that particular equation. So as you know Ft, now the restoring force, and A, we can then actually simplify this a bit further, because if we say it's for angles displaced of less than 10 degrees, we can use the small angle derivation to say sine theta equals theta. So now A is equal to minus g theta. So this is a very important idea, and it's, like I said before, derived from the small angle approximation, where it does prove to us that A is directly proportional to minus x. So this tells us that for investigations involving the pendulum, we can only really displace our pendulum by 10 degrees from equilibrium to gain our accurate results. Now again, we can use these ideas to work out the time period of oscillation for a simple harmonic oscillator. So if theta is small, we can use our right angle triangle to say that sine theta is equal to x over L, and we know A is equal to minus g sine theta. So we can substitute that into the equation and say A is equal to minus gx over L. So we also know that minus omega squared x is equal to minus gx over L as a simple harmonic motion. The x term cancels out to give us an equation for theta, and therefore we can turn that into t by saying theta is equal to 2 pi over t. So we also know that basically t is equal to 2 pi times by the square root of L over g, where L is the length of the string and g is the acceleration due to gravity or the gravitational field strength. But this only works when theta is 20 degrees or less, ideally 10 degrees or less. But you should only note the only factors in the time period equation for the simple pendulum are the length of the string and the gravitational field strength. Nothing else affects the oscillation time period, not even the pendulum mass or the displacement from equilibrium. So we know t is equal to 2 pi times by the square root of L over g, where t is the time period for one oscillation of a pendulum, L is the length of the pendulum in meters, g is the gravitational field strength of the pendulum in newtons per kilogram, and 2 pi is the constant. You are given this equation in your examination book, and the assumptions are the amplitude of oscillation is 20 degrees or less, the length of the pendulum is from the fixed position to the center of mass of the bob, and there are no dampening forces acting on the pendulum. Now we term pendulums like this as a simple pendulum. Now any factor not in the equation cannot affect the time period of the oscillation of a simple pendulum. So what you would do is you would change the length of the pendulum in the investigation, you would measure the time period of one oscillation of a pendulum, and then this allows you to work out the gravitational field strength that the pendulum is in. So what we can therefore say is if we change the length and measure the time period, we can plot a graph of time period squared against length. Now, as we know, t squared equals 4 pi squared times by L over g. So therefore, as y equals mx plus c, in this context, y is equal to t squared, x is equal to L, so therefore m is equal to 4 pi squared over g. So therefore, the gravitational field strength is 4 pi squared over the gradient. So what we can also say is if we plot a time period squared against amplitude, we get a straight line because the amplitude of oscillation does not affect the time period of oscillation, as it's not in the equation, which is a very important idea. Now also the mass of the pendulum does not affect the time period, as it is not found in the time period equation. In our next part of the video, we're going to look at force vibrations and resonance. Now, in previous lessons, we've looked at the different mathematics of the different types of oscillators. Remember, a simple harmonic oscillator is when the displacement of the oscillator is proportional to the acceleration of the oscillator in the opposite direction. A is directly proportional to minus x. So what you can categorize all oscillating or vibrating systems into two different types. System 1, a free vibrator. These are objects which oscillate freely after being initially disturbed, such as a swing. So what happens is these systems have to be disturbed initially, but then don't need a further force. So free oscillators only require an initial force. If there are no external forces applied to the system after it starts vibrating, it is a free oscillator. Whilst this tells us that free vibrators involve no transfer of energy into or out of the mechanical system, while system 2 is a force vibration system. So these are objects which have their oscillations produced when a driving force is placed on it. So a signal generator is an example of a forced oscillator. So a forced vibration is caused by a periodic driving force acting on the system. So this periodic driving force causes work to be done into the system. The force causing this movement is called the driving force. So if it's continually applied or repeatedly applied to keep the oscillation going, we have a forced oscillator due to the periodic driving force. So a simple pendulum is an example of a free oscillator, as it will continue to oscillate freely after it has been displaced. So once the initial force has occurred, the oscillator will still oscillate. Now a free oscillator will oscillate at a set frequency called the natural frequency. So here the pendulum is vibrating at its natural frequency. Now the factors that affect the natural frequency are the terms in the equations used to calculate the time period of the oscillator, as time period is 1 over frequency. So in this instance, when our free oscillator is oscillating as a free vibrator, no energy is being put into or taken out of the system. So it assumes no dampening forces such as air resistance occur in our system. Now a forced oscillator is one for which a periodic driving force acts on the oscillator affecting its oscillation. So this driving force is constantly acting on the system. So forced oscillators or vibrators can only be produced when a periodic driving force acts on the object. So it's placing energy, it's doing work into the oscillating system. So the action of placing work into an oscillator will turn a free oscillator into a forced oscillator, but it requires a lot of work to achieve this. It's much more efficient to allow a system to oscillate at its natural frequency. So if you would actually cause an object to move against its natural motion, you are producing what we call a driving frequency. But it is a lot easier to let an oscillating system oscillate at its natural frequency rather than drive it. So an example of a forced oscillator is a harmonic oscillator, as they have a motor driving them. But again, remember that a forced oscillator can only be produced when periodic driving forces act on the object. So we can summarize our situation as following. Free vibrations involve no transfer of energy to or from the surroundings. They're natural oscillators once a system is being displaced from equilibrium, and the system oscillates at its natural frequency. Whilst forced vibrators involve energy transfer into the system from a periodic driver. Oscillations in the system due to the periodic driving force take place, and the system oscillates at a driven frequency. Now in theory, you would have no energy being lost from the situation. However, that is not the case in the real world. Friction causes energy to be lost in a simple harmonic system to the internal energy of the surroundings, and air resistance can also cause energy to be transferred from the simple harmonic oscillating system to the internal energy of the surroundings. So we call these types of forces the dampening forces. Now they will decrease the amplitude of the oscillating system, but the period of the oscillation will remain the same, which is an important concept to understand. So dampening forces are resultant forces that oppose the motion of the oscillating body, so they'll slow or stop the simple harmonic motion from occurring. Now, another name for these dampening forces is dissipative forces. This is because the dampening forces dissipate energy to the surroundings, so energy is transferred from the mechanical system of the oscillator to the internal energy store of the surroundings. So these forces make the system an open system. Now, systems are often deliberately damped to stop them oscillating or to minimize the effect of resonance. Now, parts of systems which are designed to produce dampening forces are called dampeners. So systems will have these dampeners, such as car systems, so that in fact we don't have continual oscillations. So dampening systems are classified by the effect they have on the oscillating motion of the system. The first type of dampening is underdampening or light dampening. This is that dampening that slowly reduces the amplitude of oscillations but keeps the time period and frequency almost constant. So in real terms, the oscillator decreases in swinging over time. Now, most types of oscillators in the real world are light dampening. Now, the dampening effect here is very gradual, and the amount of amplitude changing each time is very small. So many systems in the real world are underdamped and will oscillate while the amplitude decreases exponentially, the time period stays the same. So examples of light dampening include a simple pendulum and the mass spring system. Now, heavy dampening is dampening that reduces the amplitude of oscillations but also keeps the time period and frequency almost constant, so the oscillator decreases in swinging over time. But in contrast to light dampening, this dampening effect is quite fast. Heavy dampening is the same as light dampening, but just it takes less time to stop oscillating, so the reduction in amplitude is greater. So this could be because the resistive forces producing the dampening effect are now larger. So for example, the object could have a larger surface area, as would increase their air resistance. The third type of dampening is critical dampening. This is when an oscillator returns to its equilibrium position in the quickest possible time without going past the equilibrium position. So it doesn't even make one oscillation. It returns to the center very, very quickly. So a critically damped oscillator returns to equilibrium position very quickly. The dampening effect is very sudden. Now, an example of a critically damped system is a shock absorber in a car, as it's advantageous to have the oscillations decay as fast as possible. Now, they don't even carry out an oscillation, they just return to the equilibrium position. Now, overdampening is when an oscillator returns to its equilibrium position in a very slow time without going past its position. So that's a very, very important concept, that it will take a long time to do this. It takes a very slow amount of time to actually work it through, to move back. So the dampening effect here is very gradual. It's the most dissipative dampening effect. Now, overdampening can be considered an extreme critical dampening idea. So an example of overdampening would be heavy doors, as this takes place so that doors do not slam shut too quickly and so people can walk through them. So there are four types of dampening: underdampening, heavy dampening, critical dampening, and overdampening. Now, all these types of dampening reduce the amplitude of oscillation over time. Generally, the heavier the dampen, the quicker the amplitude is reduced to zero, except for overdampening. Now, all types of dampening dissipate energy from the mechanical system to the internal energy store of the surroundings. Now, critical dampening is often desired because such a system returns to equilibrium rapidly and remains at equilibrium as well. And in addition, a constant force applied to a critically damped system moves the system to a new equilibrium position in the shortest time possible. Now, also, plastic deformation of ductile materials reduces the amplitude of oscillations in a periodic motion in the same way as dampening. Now, as the material changes shape, it absorbs energy, so the oscillation becomes smaller. Here you can see different graphs showing dampening. So you've got overdampening, critical dampening, and underdampening. Now, the only damped oscillators that complete a full cycle are light and heavily damped systems, not critical or overdampening. Now, when a system acts as a free oscillator, it oscillates with a natural frequency f0. If that system, when acting as a forced oscillator, has a driving frequency the same as the natural frequency, the amplitude becomes very large. We call this resonance. So this graph shows the amplitude with which a simple harmonic oscillator will vibrate against the driving frequency applied to it. Now, resonance can only act on a forced oscillator. So resonance occurs when driving frequency equals natural frequency, and it can be observed with a massive increase in the amplitude of the oscillating system. So resonance leads to a large increase of energy into the system. So here's our simplified version of a resonance graph. Now you can identify the resonance frequency of a system from identifying the frequency with the highest amplitude, as it has the highest energy store. So B here is our resonance frequency, but it's also the natural frequency of the system. Now to determine the resonance or natural frequency of the system, you've got to take many experimental points around the peak of the graph. So you decrease the intervals around the peak values. Now we know resonance occurs because the oscillator wants to oscillate at its natural frequency. So that's when it's the most stable. So this means systems can absorb energy from a driving force easily, increasing its amplitude. Now resonance can only be observed in force vibrations, as it's the driving force which is where the oscillator absorbs the increased energy from. So as far we've assumed the oscillating system is undamped. It has no dampening forces acting on it, but this isn't the case in the real world. Now resonance can only really occur when dampening is small. Dampening makes the simple harmonic energy in the system move to the internal energy of the surroundings, so dampening would lessen the effect of resonance. So dampening reduces the sharpness of resonance. As you'll notice from our graph, that if you want to lessen the effect of resonance on your system, you would either change the natural frequency of the material or you would include dampeners. Now dampening lessens the effect of the resonance spike in the amplitude, so therefore we say it loses the sharpness of resonance. So heavily damped systems have a flatter response to an increase in the driven frequency, and they don't increase their amplitude very much near the natural frequency. So heavily damped systems are not as sensitive to the driving frequency, and also heavily damped systems have a resonance frequency slightly lower than the natural frequency. So this tells us that dampening reduces the sharpness of resonance. This tells us that it lessens the effect of the resonance spike in amplitude and causes energy stored in the system due to resonance to be dissipated to the internal energy store of the surroundings. So the lighter or the less the dampening, the larger the maximum amplitude there is in resonance, the closer the resonance frequency is to the natural frequency, and when dampening is lighter, the resonance curve is much sharper. So a system can be made to oscillate with the driving force. When the driving force begins to oscillate, the driven object has a phase difference with the object providing the periodic force of 0. So the driver and the driven are what we say are in phase. So at the start of the process, the object which is driving the situation and the object which is being driven are oscillating in phase. When you hit resonance, resonance is achieved when there's a phase difference between the driver and the driven of pi over 2, or a quarter of a wave. So it tells us that the driver is pi over 2 radians, or a quarter of a wave ahead of the driven. So it's important to note that the driver is always ahead of the driven because the driver is putting the energy into the oscillating system. So at this point, the periodic driving force is exactly in phase with the velocity of the oscillating system. It's causing this increase in amplitude. Now when the driving frequency is above the natural frequency, you no longer have resonance, and so therefore the driver is pi radians, or half a wave ahead of the driven, in this case the spring vibrating. Now again, the driver is ahead of the driven because that's what's providing the energy into the system. So we can summarize the difference in the following situation. So before resonance, the phase difference between the driver and the driven is 0 pi radians. They are in phase. At resonance, the driver is a quarter of the cycle ahead of the driven, or pi over 2 radians ahead, and after resonance, the driver is half a cycle ahead of the driven, or pi over pi radians ahead. Now, let's summarize our following properties. Now, when you apply the frequency to the driven oscillator, when the driven frequency is below the natural frequency, the amplitude increases. When the driven frequency is the same as the natural frequency, the amplitude is a maximum. And when the driven frequency is above the natural frequency, the amplitude decreases. So when the driven frequency is below the natural frequency, the phase difference starts at 0 and starts to increase. When the driven frequency is the same as the natural frequency, the phase difference is pi over 2 radians. Whilst when the driven frequency is above the natural frequency, the phase differences starts at pi over 2 radians and goes to pi radians. So finally, we can show a simple setup of several pendulums showing this resonance. So what we can show is something called Barton's pendulum, which is when a heavy swinging ball acts through the suspension wire to drive all the other pendulums at its natural frequency. Now only the pendulum with the same natural frequency vibrates with a large amplitude because this is the pendulum under resonance. This is because the pendulum has the same length of wire as the driving pendulum, pendulum, and so the other pendulums show little movement because their driving frequency does not equal that pendulum's natural frequency. So this is a setup of Barton's pendulum. So pendulum X acts as the driving pendulum of the system. So as this is the driving force, at resonance this will be vibrating pi/2 radians ahead of the pendulums it's making it vibrate. Now only the pendulum with the same string length will have the same natural frequency as the driving frequency and undergo resonance. So this means the pendulum with the same string length as the driving pendulum will vibrate with the resonant frequency. So this will be observed because this pendulum would oscillate at a higher amplitude than the other pendula. So if we look at this particular setup, we've got our driving pendula providing the driving force to move the other pendula, and here are the driven pendula which are being moved by the driver pendulum. So which one would undergo resonance? Well, it would be pendulum B, as it has the same natural frequency as the driven frequency, because it has the same frequency as the driving pendulum, as they have the same length. And what affects the frequency and time period of the pendulum is the length of the pendulum and the gravitational field strength. And finally, the driving pendulum will oscillate pi/2 radians ahead of the pendulum B when it drives it, as it's leading the pendulum to give it energy. Now, as mentioned before, every forced oscillator can undergo resonance, and there are many examples of resonance in the real world, such as the example of the Tacoma Narrows Bridge collapsing in 1940 due to it undergoing resonance. So when the bridge was undergoing resonance, it observed the following features. This is because the natural frequency of the materials matched the driving frequency of the bridge due to the wind. This led to resonance occurring, and the energy store of the system increased dramatically, and the amplitude of the bridge increased. This eventually led to the bridge collapsing after it had been carried out too much stress. Now these days, engineers have to work out the natural frequency of the metals used and ensure the winds in that region do not vibrate the metals to the same frequency. Now again, in a more modern example, in the year 2000 in London, they opened the Millennium Bridge, and when people started to walk over that, they noticed that different parts of the bridge suffered from excessive sideways wobbling, and resonance was occurring because the natural frequency of the bridge was about 1.5 Hertz, and normal walking pace is between 1.6 Hertz and 2.4 Hertz, but sightseers started to move more slowly across the bridge, so it started to vibrate with its resonance, and therefore when people started to walk across in more numbers, they matched this vibration, and so it increased the effect of resonance even more. So we observed with this new bridge that we were getting this effect of resonance. So what engineers did to solve this problem is that these oscillations were reduced by the effect of dampening. So what they did is they installed dampeners into this particular bridge, which would reduce the effect of resonance, because this meant the energy store of the system could not increase as dramatically. So dampening can be an extremely useful effect in the real world. So let's summarize what we've looked at in this revision session. We know circular motion. Motion in a circular path at a constant speed implies that there's an acceleration and requires a centripetal force. The magnitude of the angular velocity is equal to omega equals 2 pi f, or v over r. We can measure the angles in radians. We know the direction of the angular velocity will not be considered as constantly changing. The centripetal acceleration is equal to v squared over r, or omega squared r, and centripetal force is equal to mv squared over r equals m omega squared r. We can then analyze characters of simple harmonic motion, know the condition for simple harmonic motion, and have our equations for simple harmonic acceleration, displacement, and velocity, linking it into graphs as well. We can know the maximum speed of a simple harmonic oscillator and the maximum acceleration. We also know simple harmonic systems such as the mass spring system and the simple pendulum. We can know the variation of kinetic energy, potential energy, and total energy with displacement in time for the pendulum and the mass spring system, and the effect of dampening on oscillations. Then finally, we can understand the idea of free and forced vibrations, understand resonance and the effects of dampening on the sharpness of resonance, and examples of these effects in mechanical systems and situations involving stationary waves. So thank you very much for watching the following revision session on periodic motion, and have a lovely day.